Hello everyone. So in this lecture we are going to uh, go forward with an implementation of whatever we had been discussing uh, in the previous lecture on the example problem illustrating uh, the Airy stress function. Now uh, I'll start a new file here. All right, and now almost the same things that I did initially while discussing the introduction to Jupyter Notebook and SymPy. I'll do it here also. So first things first, we import SymPy as Sim. We do a shift enter and it will take some time to load up. Done. So we now define our two variables x and y. That's done. And now what we are going to do is to set up our Airy stress function. You please note that when we were discussing the previous channel, when we were discussing the previous lecture, so here I mentioned that a big challenge in this Airy stress function is to choose a suitable Airy stress function. Okay, so although we discussed various things, the boundary conditions and everything here, but we never really wrote down the Airy stress function because that is a real challenge. What to choose? So because we are not very sure what to choose, we'll choose almost everything. Okay, almost everything meaning that up to the 5th degree polynomial, if we choose, then we can be pretty sure. Okay, so this is a very vague term, pretty sure, but it has been seen that many problems can be addressed by choosing a polynomial up to the 5th degree. So we'll take that. Of course, for certain problems you do have to take up to 6th degree even. But for now, for this problem, we'll take up to the 5th degree. But unlike when we do it on a piece of paper, we have to do a priori some kind of clever thinking as to what to drop and what not to drop, which terms to drop and which terms not to drop. Here we'll make no such a priori decisions. We'll take all the terms that are present starting from the 2nd degree to the cubic and the 4th degree terms to the 5th degree. Okay, so that will be a very long Airy stress function to begin with. Okay, and our hope is that by using it, by using the symbolic Python, we'll be able to systematize the whole thing and proceed towards a very general kind of framework to obtain the stress fields. Okay, so we do it in parts here. So first of all, the 2nd degree polynomial will have to do a20 x square plus a11 x into y plus a02 into y square. Of course, these a20, a11 and a02, they have absolutely no meaning currently, so we need to define them first. So a20, a11, a02 is equal to sim.symbols, just like we had done in the case of the introductory videos. So that's it. Okay, so we can also display this little bit. So that's our Airy stress function considering only the quadratic terms. Our plan is to similarly write down Airy stress functions considering only the cubic terms, the quadratic and the 4th degree terms and the 5th degree terms, and then to consider a combined Airy stress function considering all the terms. Okay. Next, for the cubic terms, a30 times x cube plus a21 times x square times y plus a12 into x into y square plus a03 into y cube. We display that as well. Next, for the 4-degree terms, we have a40, a31, a22, a13, a04. Again, we define these things: a40, a31, a22, a13, a04. Now for the a4, we have a40 into x to the power 4 plus a31 into x cube into y plus a22 into x square into y square plus a13 into x into y cube, and finally a04 into y to the power 4. Again, we display this. And finally, for the 5th degree polynomial, we have a50, a41, a32, a23, a14, a05 equal to sim dot symbols a50, a41, a32, a23, a14, so you can see that I'd made a bit of a mistake, or so one would think, by not writing the underscore here, but it kind of symbolic Python kind of intelligently understood what was going on, what I really wanted. So that's good, but nevertheless I want to make this thing explicitly clear. Okay. Please note that every time I do a shift enter in a cell, the input cell number, it gets updated. So previously it was 5, it has now become 7. Anyway, we'll proceed doing this in a systematic fashion. Finally, the A05. And for the A5, I have A50 into x to the power 5 plus a41 into x to the power 4 into y plus a32 into x to the x cube into y square plus a23 into x square into y cube plus a14 into x into y to the power 4 plus a05 into y to the power 5. And we finally display the Airy 5 as well. Alright, now all that we have to do is to combine all of them into a phi. Okay, I might have as well called that as Airy or rabbit or tiger, doesn't matter, and I just add them up. Okay, Airy 2 plus Airy 3 plus Airy 4 plus Airy 5, and I display this. All right, now the first thing that I need to ensure is that this humongous Airy stress function that I have written, what conditions must be satisfied so that the biharmonic equation is not violated. Okay, so we have to understand that the biharmonic equation, so this phi must satisfy the biharmonic equation. So what are the conditions that must be satisfied? So for that, we'll consider the biharmonic of this. Let's call this as the biharm. We'll not define a separate function, unlike the introductory thing. We'll just write down this as an expression. So sim.diff phi x4 plus twice into sim.diff phi x, x, y, y. So that will differentiate phi with respect to x twice and with respect to y twice. And finally, sim.diff phi 4, right? So we can display this also, but more importantly, because we really want to, so let's first display this actually. Okay, now you see that there are some brackets involved here. Okay, I don't want that. So what I will do is I will first of all expand this thing. Okay, just like in our introductory things. So now those brackets are gone. It's all very nice and clear and explicit. Now what I will do is, you see, if I set this to 0, because that's what the requirement is, that the biharmonic of phi, that should be equal to 0. Now that can be equal to 0 only if individually the coefficients of x, the coefficients of y, and all the constant terms, they are 0. So let's see if we can do that. So we'll need to set up 3 equations to satisfy this. So from this single equation, okay, or from this single expression set equal to 0, we are going to obtain 3 equations, one from the coefficient of x, one from the coefficient of y, and one from the constant terms. Okay, so let's try to implement that. First of all, let's say we have the biharmonic coefficient of x, so that will be biharm dot coefficient x. The corresponding equation from this, let's call this the condition 1, because that is the first condition that must be satisfied for our entire problem. Okay, so we set it up like an equation. So biharm x, that should be equal to 0. In a similar fashion, we'll have the biharm y, which is basically extracting the coefficients of y, that will be set as condition 2. This will be another equation. And finally, the biharm, let's call it biharm 0, just to denote that these are the terms which are the coefficients of let's say x to the power 0 or y to the power 0. That's what this 0 kind of signifies. And that can be done by the substitution of x0 and y0. Okay, so what I'm basically doing here is that so let me just do this thing and show it to you directly. Let me just complete this in a minute, and then I'll show it to you. So let's display the 3 conditions. Okay, condition 1, condition 2, and condition 3. So let me do a full screen here. That will be helpful. Okay, so you see, for the first condition, what I have obtained here is this 24a14, 24a32, and this 120a50. Or from the condition of the coefficients of y is set to 0, I'll have this 120a05, 24a23, and this 24a41. And finally, for this one, you see, in this equation, when I wrote this line, I wrote the biharm 0, 0. So the biharm 0 here, that is the expression that I obtain when I substitute x equal to 0 and y equal to 0 in this biharm expression. So if you set x equal to 0 and y equal to 0, this term is going to disappear. This one, this one, this one, this one, and this one. So all that will be left is this 24a04 from here, the 8a22, and the 24a40. All right. uh, and please note that those are actually originating from the 4th degree terms, from the Airy 4. Similarly, the first and the second conditions here, they are originating from the Airy 5. So these are the first 3 conditions that must be satisfied for us to be able to solve this problem. And we are going to build up more and more equations and conditions as we go forward. So for that, what we'll have to do is to take the help of the boundary conditions. Okay, so let us remind ourselves from this previous discussion, these boundary conditions. So you see, the boundary conditions are all written down in terms of the stresses, the sigma yy, the sigma xy, the sigma xx. All right. Now, those boundary conditions are specified along the various edges. All right, which means that when we have to write down these conditions, we have to first of all find the expressions, the general expressions of the stress fields from the Airy stress function, that is from the phi in our problem, and then subsequently we have to substitute appropriately for the various edges, that y equal to minus h or y equal to h, x equal to a, x equal to minus a, and then proceed. Okay, so this is going to take a little bit of time, but it's a very systematic way of proceeding. Okay, so let's do this. So first of all, sigma xx, so that will be sim dot diff phi y comma 2. Okay, next sigma yy will be sim dot diff phi x comma 2, and sigma xy should be equal to sim dot diff phi x comma y, and let's not forget the minus sign. All right, so if we display these things, you see we get these things. All right, now because we are writing down a lot of expressions, and already we are in input cell number 12, things can get out of hand pretty quickly. So it might be a good point to start writing these things down in a slightly more systematic fashion using the IPython display kind of style. So we'll do that now. So from IPython.display, import math and LaTeX, and now we are going to display our sigma xx, sigma yy, and sigma xy in a clearer fashion. So display, we'll use a little bit of LaTeX here. Let me quickly write this down. So the first one was actually a sigma xx. All right, let's see if this thing works. Sorry, I should have done that as format sim.latex. So that's better. Similarly here, sim.latex, my xy. All right. If we want, or perhaps it will be a good idea to actually write these things down as in their expanded notations. Okay, because you see that we have a bracket here which may cause a trouble if we have to manipulate these expressions further. So we want to have nice expanded versions of this. The sigma xy is already in a full expanded notation, so we don't have to worry about it. We run that again, so you see the brackets are gone. Similarly here, we run this again. All right, So now we can refer to these expressions as and when we need. Uh, so let us remind again ourselves what we are doing here. We have already found out the three conditions back here, proceeding from the requirement that the Airy stress function that we have chosen by combining the various degree polynomials, they must satisfy, or that must satisfy, the biharmonic equation. Next, we are writing down we have found out the expressions of the stress fields with the intention uh, of being able to write down the boundary conditions as we had discussed in the previous lecture. All right, so for the boundary conditions, what we are going to do is we are going to take up the edges one by one. Okay, so it might not be a bad idea to maybe use the markdown facility of writing a little bit of description before you actually uh, implement those boundary conditions through our symbolic Python code here. So I'll do an escape and press M here to change this cell to a markdown cell, and then write a little description about the boundary condition that we are just going to implement. So the first boundary condition is that y is equal to minus h. So let us remind that again. So we are going to implement this boundary condition that at y is equal to minus h, sigma yy is equal to minus q naught, and sigma xy is equal to 0. Okay. So first, at y is equal to minus h, boundary conditions are sigma yy is equal to minus q naught and sigma xy is equal to 0. So we need to do a sigma yy and substitute y as minus h. But please note that till now we have neither defined h nor defined this q naught, and that is going to create a problem for us. Okay, in fact you can do a shift enter and it will already show an error. So see, h is not defined. So what we'll do is even before this cell we are going to or perhaps before this cell we are going to define these parameters h and the load q. Okay, we'll also use that opportunity to define the length a, which will also require. Okay, so escape and we press the letter a to insert a cell just above this cell. That's it. So h comma a is equal to sim.symbols h comma a, as easy as that. However, we really want to be very sure of what we are doing here, so that there is absolutely no trouble later on. And since we know that both h and a are lengths and they are supposed to be positive, we can actually specify to symbolic Python that these are positive quantities in this, using this syntax, that positive is equal to true. Similarly, the q naught can be defined in this fashion, and that also can be set as positive equal to true. Okay, it is not necessary, but let's just do this. So I did a shift enter there, another shift enter, and now it understands what's going on. Now this is only the expression of sigma yy where we have substituted y equal to minus h, but we need to set this up as boundary conditions. All right, so what we'll do is, since this is an expression, we don't want to keep on writing this sigma yy dot subs y comma minus h. We'll call this particular expression as e1. All right, so so now we can use this e1 expression as part of our boundary condition. Okay, similarly we'll also have t2, that will be sigma xy dot subs y comma minus h. Right, So we can display this T1 and T2, but that's not necessary. Okay. Uh, what what is more important to note here is that if we just take a look at all right, let's do this T1 and T2 just for now. Okay, and let me just discuss this. You see, in this expression, the first one, which is sigma yy, where the y has been substituted by minus h, I have expressions which are devoid of any x and y, but I do also have expressions which involve x, which involve x square, and which involve x cube. Similarly, for this T2, which is basically sigma xy substituted, where y has been substituted by minus h, I have expressions which are like constants. I also have expressions which involve x, which involve x square, and which involve x cube. Now consider the boundary condition sigma xy is equal to 0, which we have written down here. Now if sigma xy is supposed to be equal to 0, then because we have this kind of a condition where we also have expressions involving x, x square, and x cube, it must be true that all the coefficients of x cube must be individually 0, all the coefficients of x square must be individually 0, all the coefficients of x must be individually 0, and all the constant terms must be individually 0. That is very, very important to note. In a similar fashion, considering T1, we note that this T1 has to be equal to minus of Q naught. Now, because we have these various terms in the T1 expression, which have x cube, x square, x, as well as the constant terms, and we have to set this equal to minus Q naught, which happens to be a constant, we must ensure that it is only the constant terms which are equal to minus Q naught, and the coefficient of x in this T1 expression, that is those are equal to 0, the coefficients of x squared, those are equal to 0, and the coefficients of x cubed, those are equal to 0. This is a very, very important point. So we'll do that immediately. Okay, so what we'll do here is instead of displaying, or let's keep that for now. Okay, so we want to find out the coefficient of x in this T1 expression, and we want to set that equal to 0. So we set that up like a symbolic Python equation, and that, mind you, will be the first part of our first boundary condition. Okay, so please note here that this is the first part of my first boundary condition. Next, the second part of my first boundary condition, that will be the coefficient of x square set equal to 0. The third part of my first boundary condition will be the coefficient of x cube set equal to 0, and the final one, the fourth part of my boundary condition, my first boundary condition will be where I substitute x as 0, because you note that in this first expression, if I substitute x equal to 0, all that will be left is just this constant terms, and I do want that constant terms to be equal to minus of Q naught. That's it. Okay, so these are the four parts of my first boundary condition, and I can actually display them also. So you see, previously I had these three conditions generated from the requirement of satisfying the boundary conditions. To those three equations are now added four more conditions based on the first mathematical boundary condition that sigma yy is equal to minus q naught at y equal to minus h. So these four equations that we are obtaining, those correspond to the actual mathematical boundary condition which we had written in our in this previous lecture. So this is what we have just implemented. Sigma yy is equal to minus q naught, and we have a long way to go before we can finish up with the rest, but we'll do that. Next, for T2, we'll have, so let's we are using these kinds of boundary conditions nomenclature BC1, BC2, BC3, BC4. We'll continue in that same vein. So here again, T2, coefficient of x, that must be set equal to 0. And let me just quicken things up a little bit by using copy paste. So again, coefficient of x squared set to 0. Next, coefficient of x cubed set to 0. That will be the third part of my second boundary condition. And finally, all the constant terms here they must be set to 0. Okay, because you note that if you just take a quick look here, the sigma xy is equal to 0, unlike the sigma yy which had a non-zero value. So all the constant terms present in this sigma xy expression, that is also equal to 0. That's what we have just implemented in this BC8, and we'll again display this BC5 to BC8. Sorry, I should have written that as a dot. All right. Next, we are going to take up the boundary condition at y equal to plus h, this one. Okay, and now this, you see that sigma yy is equal to 0 as well as sigma xy is equal to 0. So this is going to be written down very easily. We can actually so first of all, you note that till now we have not actually written down the expressions where sigma yy, in sigma yy we have substituted y is equal to h. So here in both in T1 and T2 we have only substituted y equal to minus h. That was for the top edge. For the bottom edge where y is equal to h, we have to separately write this down as T3 and T4. So T3 will be sigma yy dot subs y comma h, and T4 will be equal to sigma xy dot subs y comma h. And again we can display these things just like before. We don't have to, but just to see. Okay, all right. So again we proceed with the writing of the various parts of the boundary conditions. We had stopped previously at BC8, so next is BC9. So sim dot equation. So this time we need to use T3, and now coefficient of x, because you see here in this T3 expression again we have coefficients of x, coefficients of x square and coefficients of x cube. So we'll do that part by part. Okay, so this must be set equal to 0. Similarly for the coefficients of x square, is BC10, BC11, coefficient of x cube. Finally, for BC12, we'll have to substitute in the expression of T3 x as 0, so that we can extract all the constant terms. And again we display this. That's it. We have 4 more conditions now. So see how we are building up the various conditions that will require in order to finally solve for these coefficients, these unknown coefficients, uh, uh, a with the various subscripts. Next we take up T4. So we can just copy paste from here to make things even faster, but you have to be really careful with not goofing up these numbers. So first of all of these must be T4. This is PC 13, 14, 15, 16. All right. Next, we have to consider the two vertical edges. So let's take a quick look at the vertical edge x equal to a. So here we have three conditions, three boundary conditions: the axial force 1, the bending moment 1, and the shear force 1. Okay, so we are going to implement them one by one. So again we required to substitute in the expression of sigma xx x equal to a, similarly for sigma xy. So let's do that first. So we have reached up to T4 in the previous expressions, and we need to call this as T5. Sigma xx dot subs x comma a, and T6 is equal to sigma xy dot subs x comma a. All right, so T5 is for sigma xx at the right vertical edge, and T6 is for sigma xy at the right vertical edge. Let's display this also. And now you see that when we have substituted, after we have substituted x equal to a in the expressions of sigma xx and sigma xy, in the expressions that we obtain, we are left with terms which involve the y square, and also the y cube. Okay, in both of these we have the coefficients of y square and y cube in addition to the constant terms. So just like before, what we are going to do is, when we set this T5 is equal to 0, we have to set separately the coefficients of y square, y cube, as well as the constant terms by setting y equal to 0. Alright, so that's what we'll do sequentially. So so if we do that, okay, what I just said, if we do that, then we'll end up with just, so if we do exactly like this, okay, what I had just mentioned, then we'll end up with conditions which will not be like this, because you see this integration sigma xx dy equal to 0, it does not necessarily mean that sigma x is pointwise 0 all over from y equal to minus h to y equal to h. So I do not want to actually set the individual terms of the sigma xx to be equal to 0, or the coefficients of y square and all those things to be equal to 0. Rather, I first want to obtain this integration and then set this integration equal to 0. So if I do like before, it will be wrong. Okay, it will not be a proper. So if I do like this, okay, coefficient, where instead of this coefficients of x square and x cube, I write coefficients of y square and y cube from this T5, and then set those to 0, it will not be a proper implementation of the boundary conditions that we have written down. Rather, I have to first do the integration. So for that, I do sim dot integrate, and this is T5. This has to be integrated over y, as y goes from minus h to h, so that is written down as y minus h to h. And we must also make sure, so let's just display this. Okay, so you see this is quite a complicated looking expression, but thankfully there are no terms involving the y square and y cube. Of course not, because we have already done the integration with respect to y. But this is not in a very nice, easy to handle fashion, notation. So we need to expand this also. Okay. So now this is nicely set up, and what we'll do is we'll set this entire integration to be equal to f of fx1. So this fx1 basically denotes that this is like the axial force in the x direction, and we'll also have fx2 for x equal to minus a, so we'll do that later. Okay, but now we also need a corresponding expression for the bending moment. Okay, so what I mean to say is that I need to implement this integration also, sigma xx times y dy. So not a problem, we can do this just like this. So for the bending moment we have m is equal to and again I'm going to do a expand. Let me write that down beforehand. Sim dot integrate T5. Okay, so the T5 is basically the sigma xx expression where x has been substituted as a, but now I have to multiply this expression with y and then carry out the integration just like I had done before, from minus h to h. Okay, so lots of brackets here, but since we are working from the inside out, they should be correct. All right, and now we display this. I mean, it will get displayed automatically. Sorry, so in the previous step I need to display this f of x1, and here also I need to display this m1. Okay, now it's where I want it to be, and let us not forget the sigma xy. So that sigma xy substituted, so where the x has been substituted by a, that is stored in T6, and what we have to do in order to implement this boundary condition, the at x equal to a, sigma xy integration minus h to h dy is equal to minus q naught a. We proceed in a similar fashion. We call this v1. Again, expand. We write this beforehand so there is no trouble later on, and then sim dot integrate T6 integration from minus h to h, integration with respect to y from minus h to h, and we can display this also. Okay, all of this is fine, but we have not yet actually written down the boundary conditions. So the last boundary condition that we wrote, the BC equation that we wrote back here, was for let's see, you see there's a little bit of a mistake that is present here. I had not noticed it earlier, but thankfully I have scrolled up now. So this is BC 13, 14, 15, 16. It's not a mathematical mistake, I was just displaying this, but anyway, we don't want to be doing wrong things, even if they do not matter. Okay, so what we have done is not mathematically incorrect, we have just displayed this wrongly. Okay, now it's all right. Now the point was that the last thing that we had written there was BC 16. So now we have to start from BC 17. Okay, so BC 17 will correspond to this, the fx1. So sim dot equation fx1, that fx1 is equal to 0. BC 18 will be sim dot equation m1, that will be equal to 0, and BC 19, we take a look once more at what should be the expression for this v1 in this thing. So sigma xy dy, so that is the v1, that is equal to minus q naught a at x equal to a. So we write that down here properly. Minus q naught into a. All right, so we display this BC 17, BC 18, BC 19. All right, so we have 3 more equations. Okay, we are going to have many equations. All right, so the last edge is the left vertical edge at x equal to minus a, and we quickly take a look at that. So the first two conditions are exactly like at x equal to a, and the third one is just having a q naught a instead of a minus q naught a. All right, so what we are going to do here is uh, we can copy paste from here, but you have to be careful with the numbers that we write down, otherwise it's going to be a horrible mess. So we start from T7 and T8. So sigma xx now has to be substituted with x equal to minus a, similarly for sigma xy, and now we want to display this as T7 and T8. And just like we had done for this f of fx1, m1 and v1, we are going to do a fx2, m2 and v2. So this is fx2, this is going to be T7, similarly for our bending moment, we can copy the expression from here, being careful to change the numbers. This is my m2 and we display this m2. All right, and finally for the v2 we copy from the v1, but make sure that we change the t6 to t8. All right, so as for the boundary conditions, as before, we have to use these things, making sure to change the numbers. So we start from BC 20, 21, 22, and these are fx2, m2 and v2, and note that we change this to plus of q naught a. Okay, again we remind ourselves that the v2, this integration of sigma xy at x equal to minus a, integration of minus h to integration with respect to y from minus h to h, that is equal to plus q naught a, unlike what was at x equal to a. All right, that is what we have just implemented here, and here we accordingly display this BC 20, 21 and 22. All right, so you see we have quite a long list of equations. We have 3 here. Okay, so as you can see, this is BC 22 already, and in addition to these 22 equations, we also had those 3 conditions at the very beginning. Okay, so these 3 conditions. So our job now is to solve these 3 plus 22 equal to 25 equations simultaneously. Okay, so remember when we did that little toy example in our introductory discussion with linsolve, we'll exactly do that here. Okay, now there is a little bit of an issue here, but we'll see. Okay, we'll discuss that once we are done with this thing. Okay, so we are at the stage where we have in our hand 25 linear simultaneous equations involving the various coefficients a with the various subscripts, and we have to solve these 25 equations to obtain these values. Okay, in terms of the given parameters q naught, a and h. That's it, that's our job. Okay, the entire problem has reduced to this, to solving this linear simultaneous equations. Okay, so the way we go about doing it is to use the linsolve. Okay, so now this is going to be a little bit tedious to write, but we'll do this. BC1, BC2, BC3, BC4, 5, 6, 7, 8, 9, 10, 11. I hope you don't fall asleep. In 19, BC 20, BC 21, and BC 22. So let me just make sure that I have written all of them. 22, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and the three conditions. So overall, I have these 25 equations. Now, I need to write down what I'm actually solving for. Okay, so what I'm solving for are the various coefficients in the quadratic polynomial terms, in the cubic polynomial terms, in the 4-degree polynomial terms, and the 5th-degree polynomial terms. Okay, so this is basically A20, A11, A02. So A2 is done. A30, A21, A12, A03. Cubic is done. A40, A31, A22, A13, A04. 4 degree is done. A50, A41, A32, A23, A14, A05. All right. So that's it. The moment of truth. So whether it can solve it or not. Sometimes there are some issues, but let's just try to implement this. Okay, so shift enter, and what do you know? We have a solution here. All right. So so you see the way that we have written down here, it'll be a little bit difficult to try because you have so many things we have solved for. And many of these are turning out to be zero, as you can almost expect, because if you just go back to these equations that you have written, you'll see that some of them are identically zero. Okay, so for example, this A41. Okay, so that is zero. You go back a little bit more, you'll see this A50 is also equal to 0. And if you had solved by hand, you would have seen like how many of them, I mean it comes out so simply, but overall we have managed to do it in a couple of seconds. Like once you have written this down, it was quite tedious to write down, but no big brain work involved really. We just had to type it carefully, and the moment we press shift enter, I mean, okay, after a wait of about 2-3 seconds, we got the answer. Now we can go ahead and write this down in a very nice and clean fashion using the IPython display style. But you please note that our main job here is actually done. Okay, so the unknown coefficients of the Airy stress function that we have in our hand. Okay, answer is here in our hand, and because we now know the expression of phi courtesy the knowledge of these various values of the a terms or the a coefficients, we can go ahead and write down the expressions of sigma xx, sigma yy, and sigma xy. Okay, and those expressions would be true all throughout the domain of the beam. Okay, and this is so I hope if you try to solve this same problem by hand, the first challenge would be that there is no way you can, I mean, you can proceed. Of course, I mean, you can be infinitely patient and try to do this kind of a thing, but nobody does it like that. You take only limited number of terms, play around, do a hit and trial, see which terms you could probably wisely delete, and then proceed. Or if you really want to implement this solution, well, good luck. Now, the issue that I really wanted to point out. Okay, so I'm not really continuing here with the rest of the trivial steps which will actually give us I mean explicitly the expressions of sigma xx, sigma yy and sigma xy. That can be very well done, but what I really want to highlight here is that uh, I mean one very good power or facility that symbolic Python allows you. You please take a quick look at the coefficients that we have solved here. You see how many of them are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have solved for these 18 unknown coefficients of A with the various subscripts. And how many equations did we provide? We had provided this BC 1 to 22 plus 3 conditions, so in total 25 conditions. Okay, so we are solving 25 linear simultaneous equations which are not actually independent, so it's an overdetermined system. But even then, symbolic Python has very nicely given us the solution. So we are solving for 18 unknown things from 25 equations. So of course it's an overdetermined system, but still we are getting a nice solution out of it. Okay, so this is another great facility that symbolic Python allows us. All right, so with this I'll end this rather long discussion, but I hope that in other problems also you can use the same kind of framework with little bit of changes here and there, careful changes of course, to implement the solution. Okay, all right, so I hope this is really useful to you. Thank you very much.